Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. We are going to space again tonight for a new cruise in the solar system. Our destination is the system formed by Jupiter and its numerous satellites. We will visit several of them, not just the four main moons of Jupiter, which are very different from one another, but also smaller satellites. We will discover what the splendid features of the solar system are thought to be made of, how it interacts with other bodies, and what could be found inside and on the surface of its moons, where we will spend most of this journey. As always, you do not need to watch the video to follow along. If you wish to, you may close your eyes and forget about any worries as we embark on this adventure together. Also, we just launched a Patreon page for those of you who wish to support this project and get more of it. If you join, you will get new various things like the possibility to listen to all episodes with and without background sounds, regular bonus episodes. There are already 2 bonus episodes available, one about the history of glass making and stained glass, and the mysterious story about the man in the iron mask. You will also be able to download all these audios, and you will also have your say on the choices of topics, advanced releases, and updates on upcoming episodes. We hope to see you there soon so that we may continue developing Lights Out Library, which we enjoy so much. You will find links in the description box and the first comment pinned under the video. If you fall asleep and wish to resume the video later or jump directly to a particular part of the story, timestamps are also listed in the description and pinned in the first comment, as well as links to different streaming options like Spotify, Apple Podcasts, and Amazon Music, which may be better suited for you. But before we begin, assume a comfortable position. Take a long, deep, relaxing breath. When you exhale, release the tension in your shoulders, your neck. Release the tension in your facial muscles too, and allow the sound of my voice to guide you through this journey. As you know, Jupiter is the largest planet in the solar system and is visible to the naked eye on many nights. The first planets from the Sun in our solar system are rocky: Mercury, Venus, Earth, and Mars. Beyond the orbit of Mars begins the realm of gas and ice giants, planets that do not have a well-defined hard surface, but are giant balls of gas, becoming denser and denser as you approach their core. It is believed that underneath all these layers of increasingly hot gases, they have a solid core where metal dominates. These include Jupiter, Saturn, Uranus, and Neptune. However, rocky bodies can still be found beyond Mars, and there are many of them. Some float in a region called the asteroid belt. Between the orbits of Mars and Jupiter, including fairly large ones like Ceres or Vesta, but are not large enough to be classified as planets. Nevertheless, they follow their own orbit around the Sun. Beyond Neptune, there is also an even larger asteroid belt, the Kuiper Belt, that includes Pluto and Eris. In between these two asteroid belts, in the region of the gas and ice giants, there are many, many rocky and solid bodies of all sizes that had been captured and turned into satellites by these gas giants. Jupiter has dozens of satellites. Some are called moons because they are larger and, due to their size, tend to adopt a poor spherical shape. Others are smaller, akin to asteroids. Sometimes a few miles across or less, all the way down to small rocks and dust. Saturn has so many small objects in its orbit that they are so brilliant that they form visible rings. Jupiter also has rings, but they are not as large and are less dense, which is why they are more discreet. Along our cruise, we will land on several of the larger satellites, including the four main ones that are called the Galilean moons of Jupiter. They were observed for the first time with a rudimentary telescope by the Italian astronomer Galileo in the 17th century. But first, let's go to Jupiter. In our last cruise to Mars, I told you about the distance and how an itinerary could be decided based on orbits and the distance from Earth to Mars. Because the distances between planets are constantly changing depending on their own movement along their orbits, sometimes they can be aligned on the same side of the Sun, in which case they are closer. Or they can be on either side of the Sun, and in that case, the distance is much more. The same applies to travel from Earth to Jupiter. When the two planets are at their closest point, the distance is 365 million miles, almost 600 million kilometers. At its farthest, it is almost twice as much. Now, to get a sense of distance inside our solar system, let's bear in mind that Earth is actually much closer to the Sun than it is to Jupiter. The distance between Earth and the Sun is about 93 million miles, or 150 million kilometers. And to express astronomical distances in a simpler way, a unit, the astronomical unit, was defined as one astronomical unit is equivalent to the distance between our planet and the Sun. So, by definition, Earth is one astronomical unit away from the star, and Jupiter is 5 times farther, precisely 5.2 astronomical units, meaning that the planet and its moons receive less solar energy, and also that light from the Sun reaches them later than Earth. The sunlight needs only 8 minutes to reach Earth, but needs 43 minutes to reach Jupiter. Being farther from our star, Jupiter also has a much longer orbit than Earth, and it is slower on its orbit. Actually, the farther the planets are from the Sun, the slower they tend to be in their orbits. This is an effect of gravitation. The fastest planet in the solar system is also the closest to the Sun, Mercury, and it travels in space at almost 50 kilometers per second. That's the equivalent of more than 100,000 miles per hour. Earth travels close to 30 kilometers per second, or 18 miles per second. Jupiter is significantly slower, only 8 miles per second, or 13 kilometers per second. And so, between the longer distance to complete one revolution around the Sun, plus the slowest speed, Jupiter needs a lot more time to complete a full revolution and orbital journey around the Sun. It needs about 12 of our years. The one characteristic that makes Jupiter stand out in the solar system is obviously its large size. It is still a very small body compared to the Sun, less than 1,000th of the Sun's mass. But it is much bigger than any other planet, and even bigger than all the other planets of the solar system combined. Its mass is 2.5 times the mass of all other planets together. We will pay more attention to Jupiter later, including its composition and formation history. But for now, we are approaching its periphery, and it is time to take a look at its larger moons. As I mentioned before, there are 4 of them: Io, Europa, Ganymede, and Callisto. They are all very different from one another, and we are going to make a stop on each one. These 4 moons are the Galilean moons, as we said earlier, because they were first observed 4 centuries ago by Galileo Galilei. At the time, they were the first objects found to orbit a planet other than Earth, and their discovery was a big deal because it changed views on the nature and the shape of the cosmos. Jupiter has always been well known since the dawn of human times because it is visible in the night sky. After the Sun and Venus, it is the brightest object, but its satellites are way too small to be visible to the naked eye, so only the use of a rudimentary telescope made the observation possible. We will explore their history, their orbits, and how these orbits are in resonance with each other. But for now, let's approach the first one, Io. Io is the closest to Jupiter of the 4, the innermost and the 3rd largest of the Galilean moons. It is slightly larger than our moon, and it is a very dense body, the densest of any moon in our solar system. It also stands out for its extreme volcanic activity. There are more than 400 active volcanoes on its surface, some of which produce plumes of sulfur that climb as high as 300 miles, or about 500 kilometers. This makes the surface of Io constantly ravaged by eruptions and clouds of gas released by the volcanoes. To us, it may look almost like the representation of hell. So, why is Io so geologically active? It's because of the presence of Jupiter and its moons, but especially the mass of Jupiter, which causes a phenomenon called tidal heating. What is it? You know that rocky planets and moons in the solar system are very hot inside. Their crust at the surface solidified because it became cooler over time, and with this cooling process over millions and millions of years, the crust tends to become thicker. But there is still intense heat inside that remains trapped because of mainly 2 phenomena. First, there is the creation of these bodies when a lot of smaller asteroids and dust collided to form them. These collisions generate a lot of energy, a lot of heat, that dissipates very slowly because it is accumulated inside under the crust. Then there is a second and more important phenomenon that happens inside planets: radioactive decay. Unstable large atoms like uranium and a few others undergo fission. They suddenly reorganize their particles into smaller atoms. In the process, they liberate energy and free particles that do not get incorporated into the new atoms. This fission of unstable atoms tends to make them disappear over time, taking hundreds of millions of years for some of them, and there are fewer and fewer, but they still maintain a residual presence. Their decay, this radioactive decay, because it liberates radiation, is a natural phenomenon and keeps heating rocky planets and satellites from within. This radioactive decay also happens inside the moon, our moon, and there is most probably the same mechanism inside Io. But in the case of this body, a much bigger contributor to its internal heating is the mass of Jupiter nearby and the gravitational forces that result from it. As Jupiter is very massive, the side of Io that is closer to the planet experiences a slight larger gravitational pull than the opposite side. And due to the presence of other moons around that influence its orbit, the orbit of Io is not perfectly circular. It is elliptical. Depending on its position, the moon can be closer or farther from Jupiter. This means that as the moon is in motion, it is subject to different intensities of gravitational pull, and this force causes distortion of Io's shape, as if you had an orange in your hand and you would squeeze it, pressing in different parts. It's not going to destroy it, but it is going to flex its interior. This happens to Io, and at the scale of a rocky body like this one, it means constant friction inside the planet, which generates heat. And this is tidal heating. The gravitational pull of a large body that is strong enough to distort its satellite. As a satellite follows an elliptical orbit and moves from being closer to farther constantly. More than any moon in the solar system, this heats the inside of Io due to friction, and this is what drives its intense volcanic activity. There is a lot of energy waiting to be released, and the constant flexing of the moon makes its surface prone to moving and breaking. Apart from volcanoes, more than 100 mountains have been identified, uplifted by compression of the crust. Io may be much smaller than Earth, about the size of the moon, but it has mountains higher than Mount Everest, and between these spectacular mountains, there are rocky plains where, again, volcanism influences the moon, because lava is constantly released. Io has a relatively young surface that gets renewed with the new material coming from inside the moon. Through telescopes and cameras, Io appears in shades of yellow, white, black, red, and even green, corresponding to different types of sulfur. All surfaces on moons and planets tend to have visible craters, the remains of asteroid impacts, but Io doesn't. This is because the surface flows of lava, which can sometimes be several hundred miles long, constantly renew its surface and erase traces of impacts. There is a very tenuous atmosphere on the moon. First, because it is not massive enough to retain a thick atmosphere, and second, because Jupiter is close, as we said, and tends to steal gases from Io due to its gravitational pull. It is estimated that the atmosphere loses a ton of matter per second due to this. This is not that much on such a scale, and the faint atmosphere gets renewed by gases released by the volcanoes, mainly sulfur dioxide. As soon as they are released by the volcanoes, these gases tend to freeze due to the intense cold. The inside may be very hot, but Io is much farther away from the sun than we are. There is no atmosphere to retain heat, and when the moon passes in the shadow of Jupiter, it does not receive any solar energy at all. But when Io is exposed to the sun, a superficial layer of this sulfur dioxide sublimates, which means that it returns instantly to a gaseous state. And this is what maintains a bit of atmosphere. There would be much more to say about Io. But let's move to a second moon, one that also has exciting features, Europa. Europa presents a few cracks and streaks on its surface, but it has the smoothest surface of any known solid body in the solar system. There are very few craters or mountains. It is the smallest of the 4 Galilean moons, and it is slightly smaller than the Earth's moon. Why the smooth surface, and what is Europa made of? Its density suggests that overall its composition is similar to terrestrial planets of the solar system. Primarily, it is made of silicate rocks, that is to say, large quantities of silicon and oxygen, and its core is likely rich in metal, especially iron. But the smooth surface and other observations strongly suggests that the outer layer of the moon is made of water. Approximately 60 miles, that is 100 kilometers thick. Thus, the surface of Europa would essentially consist of frozen water ice. The question arises, if the temperatures are higher beneath this layer of ice, could there be an ocean of liquid water underneath? However, first we must understand the dynamics of this solid surface, as it features many dark streaks or lines that are visible from space. The most likely explanation is that there have been, and continue to be, eruptions of ice between plates. This ice would be warmer and erupt, causing the crust to spread open and expose the warmer layers beneath. In a sense, this phenomenon is reminiscent of the oceanic ridges on Earth that occur between plates, even though, in this case, the environment and materials involved are completely different. This is compatible with the existence of a subsurface ocean. If the ice between the crust is warmer, there may be a point where the temperature is high enough for water to become liquid. What could heat this ocean? High temperatures from the inner layers of the moon, and here, like for Io, we see the phenomenon of tidal heating that we have just discussed, which may contribute to warming the water. Surface temperatures are extremely cold, with equatorial temperatures around minus 160 degrees Celsius, which is minus 260 degrees Fahrenheit. This extreme cold is due in part to the almost complete lack of atmosphere and the fact that Europa receives less sunlight than Earth. At the poles, the temperature plunges to minus 220 degrees Celsius, and Europa also regularly passes into the shadow of Jupiter for several hours. Europa takes 3.5 days to complete its revolution around Jupiter, so for several consecutive hours it is plunged into complete darkness and no longer receives direct sunlight. At these times, the surface temperature at the poles drops to a level not far from absolute zero. In any case, the ice crust is thick, at least several miles or kilometers. However, there is an ongoing debate about the exact thickness of this crust. This is important because if it is relatively thin, there could be exchanges between the liquid ocean and the surface from time to time, for example, when these streaks form, or perhaps when an asteroid hits the moon and breaks the crust. If the ice crust is dozens of kilometers thick, the hypothetical liquid ocean and the surface would be completely separated. But in any case, the existence of liquid water on Europa is likely, and there could possibly be a significant amount of water, especially if the water layer is about 100 kilometers thick, which is the dominant theory at the moment. And even if half of it is solid ice, that would still mean a substantial amount of liquid water, which, by Earth standards, is absolutely enormous. So, if there exists a place with both water and heat emanating from the inner layers of the moon, then this raises the possibility of the existence of life on Europa. This is why, over the past few decades, this moon has been prominent among the moons of Jupiter. Following various discoveries about Europa itself, its composition, and analogous discoveries on Earth in the abyssal depths, we know that life can thrive in complete darkness, with food chains beginning with bacteria capable of withstanding very high pressure and temperature. These bacteria can feed on chemicals released by the Earth's crust, and then larger and more complex organisms feed on these bacteria. So it is conceivable that a familiar phenomenon exists thousands of kilometers under the extremely cold ice crust of Europa, in the darkness and the high pressure of its subsurface ocean. This discussion pertains purely to theoretical conditions for life that could be present on the moon. There has never been any proof of its existence. However, there are long-term projects for missions that could go to Europa to search for evidence of life. Nonetheless, even if life exists somewhere on Europa, doesn't mean its surface would be hospitable to humans at all. Apart from the cold, radiation levels are very intense, owing to the lack of atmosphere and the absence of a magnetic field akin to Earth's. Jupiter, being close, emits significant radiation. Therefore, any manned mission would have to be heavily shielded against radiation or be buried deep in the ice to find protection from this radiation. Now let's turn to the largest and the third one outward from Jupiter, which also presents a completely different environment, Ganymede. I mentioned that Europa requires 3.5 days to orbit Jupiter. Ganymede needs 7 days. Interestingly, there is an interaction between these three satellites, Io, Europa, and Ganymede, and the planet Jupiter. The three satellites are in orbital resonance. Their orbital periods are synchronized. Europa takes exactly twice as much time as Io to orbit Jupiter, and Ganymede takes twice as much time as Europe, which is exactly 4 times as much time as Io. They are in an orbital resonance of 1, 2, 4. What is this concept of orbital resonance, and why does it occur? As you know, all planets in the solar system orbit around the Sun, which has by far the largest mass of any object in our system. In fact, the Sun accounts for more than 99% of the matter in the entire system. But the Sun is not the only body that influences orbits. Even though they are smaller, planets also exert influence over each other. This depends on their masses and the distances between them. So it is correct to say that the Sun determines all orbits because it is by far the biggest factor. But if we delve a bit further into detail, saying it is 100% accurate is not entirely true. Other bodies, every body in fact, has a small influence on every other one. A large planet can distort the orbit of a smaller body and, eventually, modify it so much, revolution after revolution, that this object may be placed in another orbit or even expelled from the solar system. This has probably happened many times throughout the history of the solar system. This is a phenomenon that can greatly increase the influence between two bodies in space when they exert regular, periodic influence in each other. For comparison, think about when you are pushing a child on a swing. The swing has its own frequency, but even without touching the ground, the child can amplify the movement by pushing with their body. Because this pushing acts in periodic repetition, it has a cumulative effect on the motion. On a larger scale, this is what can happen between planets or moons orbiting a planet, and this phenomenon is called orbital resonance. Very often, this mutual influence is unstable. The two bodies exchange momentum, which progressively shifts their orbits to the point that the resonance disappears. However, under certain circumstances, a resonance system like this can become stable because it is self-correcting. The exchange of momentum between bodies keeps them in a stable resonance. This is the case, for example, between Neptune and Pluto, which are in resonance of 2 to 3. It means that when Neptune completes precisely 3 revolutions around the Sun, Pluto does exactly 2. The same kind of resonance formed between Io, Europa, and Ganymede in a ratio of 1 to 2 to 4. When Ganymede does 1 revolution around Jupiter, Europa does 2 and Io does 4. Another effect of momentum and gravitation that applies to Ganymede is that the Moon is also tidally locked to Jupiter, meaning it always presents the same face to the planet. Most moons have this characteristic. They don't rotate on themselves, similar to our moon, where we always see the same face from the Earth. But now let's take a closer look at Ganymede itself. What stands out most about Ganymede? It is the largest moon in the solar system. Its diameter is only 40% of Earth's diameter, but it is larger than the planet Mercury, although not as massive, because Ganymede is made of lighter materials, lighter elements. Mercury contains a lot of metal, whereas it is estimated that Ganymede has a core of metal and rock, but is also half made of water in different states, including various types of ice. I'll come back to this, and perhaps among them there could be liquid water. So, as with Europa, there is speculation about the possibility of life in the oceans of Ganymede. It looks less likely or harder to prove for several reasons. First, because the outer layer of ice is much thicker than on Europa, making reaching the liquid parts very difficult, almost impossible at the moment. Additionally, it is uncertain whether the bottom of this subsurface ocean reaches the rocky mantle underneath. It is believed that there is another layer of ice, but not the same type we are familiar with on Earth. On Earth, we essentially know ordinary water ice, which forms under certain conditions of pressure and temperature, typically when the temperature drops below 0 degrees and at sea level pressure. But if the pressure is higher, a lower temperature is required for water to freeze. Now you know that ice is a crystalline form, meaning that water requires a highly ordered microscopic structure. Billions and billions of molecules become perfectly ordered, following a pattern. This almost never happens on Earth due to the conditions of temperature and pressure present on our planet. However, there are different possible crystalline forms, or patterns, that water may adopt. These different crystalline structures have been explored and studied in laboratories, showing that various types of ice may exist. Ordinary water ice is called Ice 1, and many other structural possibilities have been identified, such as Ice 2, 3, 4, Ice 5, and so on. It is believed that the inner layer of ice in Ganymede is Ice 3, which forms when liquid water is exposed to temperatures of -20 to -30 degrees Celsius and a pressure of 200 to 300 times the sea level pressure we live on Earth. On our planet, these conditions can only be replicated in a laboratory because, naturally, where there is enough pressure at the bottom of the oceans, the temperature is higher than that, and where the temperature is low enough, since -20 to -30 degrees Celsius is perfectly achievable in the winter in many parts of the world, there is not enough pressure because it is at the surface. So these conditions are not naturally met in our environment, but it seems they are in the depths of Ganymede's oceans. At its surface, Ganymede is primarily composed of water ice, but there are other elements that likely arrived as a result of impacts with smaller bodies. 1/3 of the surface is dark, covered in clays and organic compounds that are believed to be traces of impactors that collided with the moon. Contrary to Europa and Io, Ganymede's surface is quite ancient on average because there is not much geological activity to renew it. However, there are still grooves and ridges that are not completely explained at this point. Given the structure of the moon, these features could have appeared many hundreds of millions of years ago, when its surface was more active than it is now. Ganymede may have a lesser chance of harboring life than Europa, but when it comes to human presence and exploration, it may be a bit more welcoming. There is less radiation due to the longer distance from Jupiter, and also thanks to a degree of protection from a magnetic field that seems to be generated, like on Earth, by the dynamo effect of a rotating metallic core at the center of the moon. The level of radiation is still deadly, and the temperature and pressure are very hostile. But with adapted protections, it is not impossible to think of a human base one day on Ganymede. Out of the different moons of Jupiter, Ganymede presents a less challenging set of conditions than Io and Europa. But there is still something even better: Callisto. We still have a fourth Galilean moon to look at. Callisto is the fourth of them by distance to Jupiter, and thanks to this, it has the lowest radiation levels. However, there are other interesting features that distinguish it. I mentioned that the surface of Io and Europa were fairly young in astronomical terms, that is to say, still millions of years old. But in contrast, Callisto has the oldest solid surface in the entire solar system. It seems that since its formation, there have never been any kinds of subsurface processes, like volcanism or plate tectonics, that could have regenerated the surface. So it has never changed at all, except for impacts. Callisto has the most cratered surface in the solar system, completely covered in impact craters that have appeared over probably several billion years. So, why is Callisto so inactive geologically? It is believed that this is due to its formation history. Callisto would have formed very slowly from the accretion of smaller rocks, but not fast enough to reach a high temperature inside. As a result, the moon is not fully differentiated internally. What this means is that bodies of a certain size, planets or large moons, tend to have a structure in layers internally. The heavy elements converge toward the center, to the core, and various elements above it form layers that are fairly distinct in terms of chemical composition and conditions of temperature and pressure. This is the case for rocky planets like ours and the first 3 moons we just visited. The process of differentiation is never 100%, for example. There can be movements in the mantle of a planet that can cause small quantities of metals to go up and reach the surface. But still, large bodies acquire an organized overall structure, one that is differentiated. However, this process was very incomplete on Callisto, making it the largest body in the solar system that is not fully differentiated. The elements inside are mixed up. There are several layers made of rock and ice mixed together. Here again, the various conditions mean that the structure of ice differs depending on how deep it is inside the moon. The crust is made of ice, 1, the ordinary one on Earth, but inside it is believed there is also ice 5, 6, and 7 with different crystalline structures, and under tens of miles of icy crust, probably yet again another ocean of liquid water. That has been isolated from space for billions of years, since nothing ever happens on the surface of Callisto except for occasional impacts that do not reach beyond the icy crust. After the Earth, Moon, and Mars, Callisto is a possible target for manned missions one day, clearly not in the 2020s or 30s. It is way farther than Mars, and there is no specific project now. But if one day humans set foot on one of the moons of Jupiter, it is likely to be Callisto first. The low radiation level and the geological stability are advantages, and Callisto would be a good base station for further exploration of the solar system and remote exploration of Europa in the search of traces of life, for example. And until now, we have spoken about the 4 main moons of Jupiter. Then there are many more of smaller sizes that were discovered long after. You remember that Galileo observed these 4 moons in 1610. It took almost 3 centuries until the end of the 19th century to start discovering more and smaller moons. Today, at this point, 79 moons in total have been found and named. They are called moons when they are large enough, and there are also moonlets and dozens of smaller satellites. Together with the planet, they form a system called the Jovian system. We'll take a look at some of these smaller bodies and also at the rings of Jupiter. But before that, let's take a look at the planet itself. As you know, Jupiter is by far the largest and most massive planet in the system. It has 2.5 times the mass of all other planets combined. It is also probably the oldest planet in the system, the first to form according to current models of planetary formation. These are theories based on our knowledge of the history of the solar system and physics, not absolute certainties. But the dominant models right now suggest that Jupiter formed quite far from the Sun, beyond the limit called the snow line. This is the distance from an early star where it is sufficiently cold for volatile compounds like water to condense into solids. The origins of Jupiter would have started with a large solid core, one of rock and metal, that would still exist today at the center of the planet. Around this core, huge quantities of gas like hydrogen and helium would have aggregated, kept together by gravitation. After a few million years, which is short at this scale, the various other planets of the solar system were not formed yet, and the system was essentially a gigantic disk of gas and dust, with a newborn star at its center. So, rather quickly, Jupiter gained enough mass to absorb everything in its orbit, to clean it up, and reach a mass that was already 50 times the Earth's mass. Nowadays, after absorbing more gases and rocky bodies, Jupiter is more than 300 times as massive as Earth. But because it is less dense, being primarily made of gas, it has 1,300 times the volume of Earth. However, the fact that it is a gas planet doesn't mean that it's like a cloud that could be crossed easily. The more you move towards the center, towards the core, the denser and hotter the planet becomes. Due to the mass, temperatures, and pressure inside, Jupiter's reach levels that are way higher than at the center of the Earth. And the gravitational forces that keep the planet together are very powerful. Jupiter's composition is dominated by hydrogen, constituting about 3/4 of its mass and 90% of its volume. There is so much matter that the interior is strongly compressed. This compression generates heat, and in fact, Jupiter emits more heat by itself than it receives from the Sun. However massive Jupiter may be, it is still not enough to ignite the same reactions of fusion between hydrogen atoms that happen inside the Sun, which is why it didn't turn into a star. We know that there are systems where more than one star forms, even though this is not the most frequent case. If Jupiter had gained more mass, it could have turned into a second star alongside the Sun, but the planet stayed well short of that threshold. It is estimated that it would need to be 75 times more massive to ignite fusion. So, because it is a gas planet, there is no solid surface to land on. As the planet begins as a cloud of low density and becomes increasingly dense, if we were to enter this giant gaseous sphere, we would reach a layer of liquid hydrogen, turned into liquid by the rising pressure, followed by another layer of so-called metallic hydrogen, another phase of hydrogen. This doesn't mean it turns into metal in the usual sense of the term, but under such conditions, hydrogen behaves like an electrical conductor, which is why it is called metallic hydrogen. Jupiter and also Saturn, which contain a lot of this metallic hydrogen, form due to their large masses that compress hydrogen. Visually, when we look at Jupiter, we see several bands or belts of color, different colors that are segregated all around the planet. There is also a giant spot. These bands move at different speeds and are made of clouds of ammonia that float in the upper layers of the atmosphere. Their movements cause strong turbulence. In its upper layers, Jupiter has powerful winds. The various bands have different circulation patterns. They move at different speeds, and their interactions create turbulence and even storms. This is what the Great Red Spot is believed to be: a vortex, a storm, that probably did not always exist but has become a stable feature of Jupiter's atmosphere. Given Jupiter's size, the red spot is bigger than Earth and rotates counterclockwise in the opposite direction to the band of clouds. The phase of fast growth is long over for Jupiter. There is no longer much matter to aggregate like in the early stages of the solar system, but the planet keeps attracting bodies like comets, which are captured by its gravitational pull and fall on it. Jupiter is estimated to receive about 200 times more asteroids and comet impacts than Earth. For a long time, it was believed that Jupiter played an important role in shielding rocky planets, including ours, from asteroid impacts. It was thought to have acted as a gravitational well located at the limit of the inner solar system, being the first and biggest of the giant planets. So Jupiter would have behaved like a vacuum cleaner for the system, but this view is now more disputed. Due to its mass, Jupiter could attract more asteroids and comets, drawing them from the Kuiper Belt, a large belt of asteroids that exists beyond Neptune. However, this debate is still open, and it is uncertain at this point whether Jupiter serves as such a shield for Earth. In any case, due to its mass and age, Jupiter has the largest number of large satellites of any planet in our system. It also has rings. These rings are not as obvious as Saturn's and were only discovered recently in 1979 when a space probe, Voyager 1, explored the Jovian system. These rings are not as large comparatively as Saturn's, and they are much less bright, which is why they weren't seen before. Saturn's rings contain a lot of ice that reflects light, whereas Jupiter's rings are primarily made of dust. In between or around these rings, there are dozens of moons. As I mentioned earlier, Jupiter has 79 moons total, So let's explore a few of them. The Jovian moons, other than the four largest ones, began to be discovered in 1892. Being much smaller, they were harder to identify from Earth. Initially, they were given numbers such as Jupiter 5, 6, 7, and so forth. Jupiter 5, also known as Amalthea, is the fifth largest moon, and the last one to be discovered by direct visual observation. The subsequent moons were found by photographic or digital imaging, meaning they were seen on photographs of space using extended exposure time, which allows the capturing of objects that may not have been noticed otherwise. Like other smaller moons, Amalthea interacts with Jupiter's rings, which contain dust ejected from the surfaces of these moons. Amalthea isn't large enough to acquire a spherical shape, so it appears irregular. Its maximum length is about 160 miles or 250 kilometers. Placed near Earth, it would appear around the size of Massachusetts or Belgium. Amalthea is believed to have formed far from Jupiter due to its lightweight structure and content of water ice. In the early stages of Jupiter's formation, the planet emitted a lot of heat. Based on the moon's proximity to Jupiter, this moon would have entirely melted. So the prevailing theory is that Amalthea formed farther out in the solar system and was captured as a satellite afterward. Visually, the moon appears very red, possibly due to sulfur collected from Io, which could explain its glow, but this is uncertain. Amalthea orbits at only 180,000 kilometers from Jupiter, which is marginally more than the diameter of the planet itself. From the moon, Jupiter would look enormous, appearing 8 times bigger than our moon appears when viewed from Earth. When we watch Jupiter in the night sky, there is one moon even closer than Amalthea, Jupiter 16, also known as Metis. It is the innermost known moon of Jupiter, orbiting at only 130 kilometers, which is less than Jupiter's diameter. Metis is the fastest moving moon of all, orbiting at a speed of 30 kilometers or almost 20 miles per second. This moon is far too small to be spherical. Its maximal length is 60 kilometers with a width of 40, so it resembles a large asteroid. Metis resides right in the middle of one of Jupiter's rings, which is not a coincidence as dust from this moon generates the ring. When Metis experiences impacts with rocks, material can easily be ejected due to the moon's low gravity. In addition to Amalthea and Metis, there are 2 more moons, Adrastea and Thebe, that possess irregular shapes. Beyond these, there are 70 other, smaller moons that orbit considerably further away Jupiter. These celestial bodies likely had their own orbits around the Sun, much like asteroids from the asteroid belt, but were captured by Jupiter over time. These moons float in space, away from the rings, and are only a few miles across in some cases. Some of these remote moons follow a prograde orbit, moving in the same direction as Jupiter's rotation, while others are retrograde, moving in the opposite direction. More satellites are likely to be discovered in the future. Currently, more than 20 of these small, irregular satellites have not been named and have only been assigned numbers. Discoveries continued to be made as recently as 2020. More moon candidates were found orbiting far from the planet. The total population of moonlets could number in the hundreds, depending on the size criteria established. So, we have reached the end of this little exploration of the Jovial system, and it is now time to return to Earth. I hope you enjoy it, and you can now fall asleep. Or you can pick out another story. And until we meet again, good night. Sleep well.